then just last week again, Atlas published another analysis using, again, the star decays. Again, their measurement is shown by this black line. It's very consistent with 0 plus and almost inconsistent with 0 minus. So it certainly does seem that if it is a spin 0 particle, it's probably a scalar. So, is it elementary or composite? So as I mentioned, there's been a big discussion about this between theoretical physicists. On the left, people think that it's elementary, probably accompanied by supersymmetry. I won't go into the details of that. On the right, people suggested it might be a composite particle, just like, say, the pion in QCD. This was unfashionable for quite some time because people thought that it would predict a very heavy scalar particle, not a relatively light scalar particle that's apparent to be seen. But you can construct models in which you get a light composite particle. So then what you can do is you can say, okay, well, let's keep an open mind, let's look at this light particle that's being seen and see whether its couplings are similar to those in the standard model or whether they're different. So basically what this means is to look at the two bottom lines on the t-shirt and you can, for example, put in a factor C, which allows for the possibility that this term might be slightly different, or factor A, which allows for the possibility that this term might be slightly different, as could happen if you've got a composite particle. So this has been looked at by various groups, including CMS collaboration published an analysis, also Atlas have published an analysis of their own data. So together with my student Kevon Yu, we've been doing a global analysis of all the data coming from Atlas, CMS, and the standardized Clevertron experiments. So we're here in the horizontal axis, we've got the parameter A, that's the coupling to vector bosons. Vertical axis, we've got the coupling C to fermions. The little black star is what you would predict in the standard model, and these yellow lines correspond to various different composite models. So this was an early analysis that we published back in April. Then in the summer, when all the new data came out, we combined all the data from the different experiments, and we came up with this picture here. So the standard model star is just on the edge of the 68% confidence level region, and okay, well, this yellow line here corresponds to this particular model that seems to be excluded. This model up here or this model up here, consistent with the data, but only if they look very much like the standard model. And this is a further update that we did using the data from the Kyoto conference last month. So I would say that, of course, we can't tell whether it's an elementary or composite particle, but at the moment it looks rather like the standard model used by them. So then, sorry, let's skip this. So does it couple to particle masses? So this was another analysis that we did where we parameterized the couplings to matter particles scaled by the power not 1, as we did in the standard model, but 1 plus epsilon. And we allow the overall scale to be different from what it is in the standard model. So the standard model prediction is represented by these crosshairs, and this bright spot represents the experimental fit, which is indeed very close to the standard model. So paper on the subject, this new particle certainly walks and quacks like a Higgs boson. So the one place where there may be some discrepancy is in the quantum loop corrections. And here you see that there's perhaps a hint that in particular coupling the photons may be larger than it is in the standard way. I would personally say that this is still a question mark, but this is certainly something that everybody is now following very closely. In the long run, of course, the self-couplings of this particle we have to wait quite a number of years. So, I'd like to conclude this sort of physics discussion by telling you a little story about when Mrs. Thatcher came to visit CERN 30 years ago. She's the one on the right. So she was introduced to a few of these physicists. What do you do, young man? I explained, well, I'm a theorist. My job is to think of things for the experiments to look for, but then I hope they find something different. Mrs. Thatcher was a bit puzzled, because Mrs. Thatcher liked things to be the way she likes them to be. Wouldn't it be better, young man, if they found what you predicted? So I said, well, actually, no, because then we wouldn't feel that we were going to learn anything. What we really hope for is something which is at least a bit different from what we predicted. So in the same spirit, I think that we all hope that although this is a Higgs-like boson, it may not be exactly the Higgs boson of the standard model. For that, we have to wait for more experimental results.
I really enjoyed the talk, John. It's absolutely wonderful, and I think spot on for what we wanted. It's open to the floor for questions.
Okay. Sorry, I heard that the actual mass that they found the Higgs at severely constrains the models that they were looking for supersymmetry. So, I mean, it hasn't been ruled out as sort of just constrained.
Right. So, in fact, supersymmetry, which I just mentioned very briefly a couple of times, is a theory beyond the standard model that predicts, gives you some range where the Higgs boson might be. And that range was actually below 130 GeV. So I would actually regard it as a tremendous success for supersymmetry that the Higgs boson has apparently been discovered in that mass range. Now it's true it's been discovered towards the top end of that mass range. So that suggests that if indeed supersymmetry is the right theory, then supersymmetric particles are probably relatively heavy. I didn't have time in this talk to show you a quantitative analysis of that. So I think that, of course, people are disappointed that supersymmetric particles haven't yet appeared at the LHC. But if you take the Higgs mass measurement seriously, then you wouldn't have expected them to. Right? But this is an open possibility when the LHC restarts at higher energies and the orbits for larger supersymmetric masses, then you could find it.
Okay. Anyone else? Yes.
Can you tell us a little bit about opportunities for graduate students at CERN?
Right. So I got a whole bunch of slides on that. So this sort of quantifies the statement that science, at least particle physics, is ever more global. And this shows you the geographical distribution of the 10 or 11,000 scientists who are registered and working in SET. And so blue countries, those are the member states. Europe basically built the accelerator. Many other countries involved in building the experiments and, of course, now in analysing the data, including South Africa. Okay. And as I was commenting to Simon just before the talk, every time I upload a new version of this map, and you can see this is a pretty recent one, the number of physicists from South Africa goes up. It's pretty impressive the way that it's been growing. Obviously, personally, I'm very sad about the fact that so far there's not so many scientists coming from other African countries. I should say that this is actually people registered as coming from institutions in the respective countries. So we've got official relations with several universities in South Africa, but so far not the same level with countries. But this is something we want to work on. So we have those training programs. We have, for example, a program for high school teachers, and this is something which I personally would be very keen to expand. Maybe we could discuss how to expand this program in the future to include more teachers from South Africa. We have a program for undergraduate students to come during the northern summer. So that's basically July and August. And we've had a number of South African students over the years. I think we had 2 last year. And we'd be very happy to see more undergraduate students coming in the future. Maybe some of you guys here to find a way of doing these within this program. Then we have various schools for graduate students. For many years we've had one in Europe. We've also for some years been operating one in Latin America. This year we started one in Asia, and CERN has been one of the institutions sponsoring the African School of Physics that have taken place over the last couple of years, and I'll come back to that in a moment. So, this is actually a geographical distribution of the summer students that we had in 2012, and as you see, we have a couple from South Africa, one from Madagascar, we had one from Ghana. We certainly open to students from wherever they may come, and as I said, we're particularly interested in developing a relationship with South Africa by having more students come in July and August of this.
So John, just before you leave the South Africa one, you capped how many you would support, which I think is 1, but you capped how many we could support.
No.
And the thing is, there's not enough applications from South Africa. Sometimes we even fail to send someone when there has been funding.
So, you guys should work on it and make sure plenty of enthusiastic applicants. And, I should remind people this program takes place in July and August. July and August actually it's kind of warm in Geneva. Right now there's snow, but July and August, that's the time to go visit. So that's something that we certainly are keen to push forward. The teacher training program, this is a summary. This is something that we started back in 1998. And this is a distribution of all the high school teachers that we've had from countries around the world during the years in which the program has been operating. And here we've had some high school teachers in South Africa. We also got special funding from the American to invite more South African high school teachers, what we could also do is teleconferences, something that we do regularly with high school teachers and their students from other countries. For example, some years ago, we had a teacher from Ghana, and on a couple of occasions, I've participated in Skype video conferences with his school, talked with the students, and it was very exciting for me this July when we had the second African School of Physics that I went to visit the school and meet the students in person. That's something we can also do. And this is sort of a summary of all the relations that we have with various different African countries. So in South Africa, we've got lots of different colours here corresponding to various different types of collaboration we have in South Africa. We're certainly keen to develop it further. As I said, one of the institutions supporting the African School of Physics. The first one was held in Stellenbosch in 2010. This is a picture from one in 2012. Simon has been very supportive of this. Unfortunately, we didn't overlap when you were in Ghana, and when I took the picture, surprise, surprise, I found the picture with myself in it. I'm with you. So anyway, I really need to answer the question.
Okay, thank you very much.
Any other questions, folks? Yes, Richard?
John, it was said that with the discovery of the electron, it was felt that it was too small to have any practical application.
Right.
Now with the discovery of the Higgs boson, like particles, do you think, can you foresee or even sort of postulate any possible kind of application? Would you end up levitation devices?
I can't see anything myself at the present time, but just as the fact that Thomson discovered the electron in 1897, I don't think anybody understood what the applications of that would be. But now I've read that in the early 2000s, it's estimated that 37% of the US economy was built upon quantum physics. I'm not saying that in the year 2112, 37% of the South African economy will be based on Higgs physics. But I just think we just cannot tell where knowledge will lead us.
Anyone else? I saw the blogger had that area, I think it was, I think it's 235 for the mass of the resonance that's sort of popping up a little bit in the mass of the Higgs. And at the Kruger 2012 workshop, I was rather surprised that the CMS speaker pointed that same thing out in a kind of wasn't sure if it was semi-official or not, because these talks have to be approved by their collaboration, and they go to great lengths to approve these talks. And on several times the CMS speaker drew our attention to sorry, 135. I think it was your next slide. Yeah. Yes.
Well, yeah, there's a little bit of a wiggle there. I don't know. Let's wait and see.
Yeah.
I'm sure that that was not an official hint and a nudge. As you can see from this, at least back on the 4th of July, this wiggle of 135 was less than 2 sigma.
It was popping above 2 sigma on the CMS slides that they showed.
Maybe things have moved on.
Yeah.
So it's certainly possible. Yeah.
Oh, so I just have a curious question about the micro black holes. Because the black hole itself, we think, of its mass being essentially a singularity, like very, in terms of
radius, which is related to the mass. Okay. But the relationship between the two is given by the effective Newton constant. So Newton constant normally we think of as 1 over n Planck squared, where n Planck is 10 to the 19 GeV, very, very small. However, these people who play with extra dimensions, they suggest that when you go to higher energies, the gravity basically leaks into those additional dimensions, and that has the effect that gravity could actually become a lot stronger at the TeV energy scale than you would naively expect. And that would correspond to the statement that the effective Newton constant changes and becomes much larger. And so that's what enables you to imagine getting two quarks inside that Schwarzschild radius, because it's much bigger than you would have thought. Okay. In fact, it would be something of the order of an inverse TeV in size in some of these things, which is, let's see, 10 to the minus 16, 10 to the minus 17. Now, I must say personally, I'm a little bit skeptical about this whole idea, but something which is not impossible.
Questions, folks? Okay, well, then we want to thank John again for an incredibly good talk